Okay, so I guess we could go ahead and get started. And as always, if you have anything you want to discuss further, let me know.
Yeah,
Uh,
okay.
Last time we were looking at simple normal regression and how we could think about this in a Bayesian point of view. And as you can see, today we're looking at evaluating those regression models. By linear regression, of course, we have a mental image of something like we have on screen right now. And we're going to continue with the bikes data set, which was a bicycle ride share program in Washington, D.C. In this chapter, the authors wanted us to consider whether a model is fair. What I thought we'd do today is also briefly discuss some data science ethics, and then we'll spend time talk about a model's posterior predictive accuracy. When we look at the Bayesian model results, that it's nice to have those numbers, but whenever you do research, it's important to also consider some of these other notions, such as how is the data collected, by whom and for what purpose was the data collected, and how might the results of the analysis or the data collection itself impact the individuals and society. When we conduct research here in the United States in our universities, we actually have to answer these questions in advance as part of our research approvals, or what's called IRB, and before we could publish our papers, and sometimes even before we even do our analyses or data collections. This is to protect people from the effects of the research projects as much as possible. And part of the considerations is maybe in eye-catching way is just to protect people from the very far-reaching effects. And we tend to see that these days in biases that come up in our machine learning projects, or in machine learning that's been applied at some larger scale, say at a company or a city. So we might ask ourselves what biases might be baked into this analysis. And here are some of the examples that were mentioned in this particular textbook, but also by a lot of people who are doing machine learning these days. For example, in this first example, in an article written by Daston, there was a computer model used by Amazon that was trained to go through and look at resumes. It is motivational that a company receives hundreds, if not thousands, of resumes for a job application. So it is tempting to have a computer program look at them and start to do the vetting process. However, as the bar charts on the screen imply, a lot of the training data historically was dominated by men over women. And what happened with Amazon's model is that they found out quickly that the computer program would recommend male candidates much more often than female candidates. And thus the company realized quickly that they need to not use that particular program. In this example, written by Harmon for Slate, the city of Detroit in the United States implemented a program where when you talk about people who might have been in prison and were being judged as whether or not they were able to leave prison and become part of normal society again, they found that in the usual years, the judges, the human judges that would make these decisions would approve the release or the end of the jail term about maybe 48% of the time. However, as the city implemented the computer program, all of a sudden the procedure only approved the jail inmates about 7% of the time. And they found that the system would heavily punish people who had some characteristics such as a darker skin color. And thus there are places that have experienced racial bias because of the way that the machine learning was done. And similarly, in the third example of this New York Times article by Heart of Us, when talking about immigration and refugee statuses for many people, the automation was used in places, but many of the systems had bias in the training data, and that affected the results as well. So these are popular examples that came up in the news media in recent years, say in the past 5 years. But as I mentioned before, that's kind of the motivation of why we need to consider some of these ethical points here when we're conducting our research, whether it's for moralistic reasons or whether or not you literally have to consider the ethics. All right, we'll come back to some of the maybe more mathematical issues here. We've been working with regression models built on normal distribution assumptions. And we're going to focus on these 3 assumptions that you see in front of you. We'll call assumption 1 the structure of the data. In particular, are the data points independent from each other? We'll call assumption 2 the structure of the relationship. In particular, we have been dealing with linear regression. And we'll call assumption 3 the structure of the variability. That is, we assumed normally distributed data, and we hope that the data or the results, well, we hope the results around a particular data point on the regression model will be normally distributed because that's how we built the system. But also we hope that this lines up, of course, with the real world data or the underlying data set. Bringing back or coming back to our case study, remember that the response variable, capital Y, is the number of bike share rides, or I might simply say the number of bicyclists or bike riders. And in our predictor variable X, we had the temperature on a certain day. We are building a regression model, intercept, and the slope for the coefficients. So B naught plus beta, so beta naught plus beta 1 times the predictor variable. And remember, maybe compared to a frequentist point of view that we might have seen in an introductory statistics class, we are predicting a mean, so to speak, but at each value of X. So this estimated mean value is coming from the regression model. To turn this into a Bayesian model, we must incorporate the prior models for each of the unknown regression parameters. That is, remember, we're looking for beta naught, beta 1, and the standard deviation. And we did briefly mention that this assumes independent inputs, where the inputs themselves are normally distributed. Now, as we might say in an introductory statistics course, we consider the sample size. The sample size here was 500 daily observations. So we, by the central limit theorem, could reasonably be assured of ourselves that we do have normally distributed data, or at least something pretty close to a normal distribution. Now, something to consider is that the response variable Y is likely to be correlated with the predictor X. That is, when we look at the data, here we have the temperature on the horizontal axis, the number of bike rides on the vertical axis. The data seem to have a positive correlation. Now, that correlation might be coming from the time of year and other aspects. And at this point, the authors noted that knowing the temperature on 2 subsequent days, like because the temperature may increase between 2 days, may decrease between 2 days, might in some sense cancel out with the time correlation in their ridership data. So in other words, the authors felt that we did not have to worry so much about the day-to-day changes in the temperature or the number of rides. So in particular, we're looking for independence in our predictor variable. So for now, the author said the temperatures are independent from the neighboring, the day previous or the day before. And especially if you go over a larger time scale, such as months, that the data from 1 month to the next are not going to be very dependent on each other. Me personally, I'm a little more hesitant about this because, especially if we are using Markov chain Monte Carlo methods at times to make our models, the Markov chains themselves assume dependence, at least for one step back in your data. I'd like to thank the previous cohorts for making these wonderful flow charts in the diagram R package. This is a good reminder that assumption 1 was talking about independence. So again, what we are assuming right now is that for the predictive variable X, the number of rides is independent from day to day. Once again, with the regression models, we are looking for the centered value of the intercept. That's the motivation for this slightly new notation here, beta not, but with a lowercase c to remind ourselves that we're centered, as opposed to maybe having a skewed left or a skewed right distribution. The normal distribution is symmetrical in that matter. Remember that then also beta 1, the slope, and the standard deviation were also prescribed distributions as well. We have another glimpse at the original data set to remind ourselves what kind of numbers we're looking at, and that's part of the reason why these numbers were chosen in the previous chapter. Now, looking at assumptions 2 and 3, which the folks in the previous cohort had labeled here in a nice figure. Assumption 2, linearity. Assumption 3, normality. We'll once again look at the scatter plot. In assumption 2, we are quickly asking ourselves, does linear regression make sense here? That blue line is the linear regression model, and we're asking ourselves, does that seem to do its intention, which is to summarize the data? And the answer seems to be that yes, the linear regression seems to be reasonable here. Then if you visualize any vertical slice of this, say what happens at 60 degrees Fahrenheit, or what happens at 70 degrees, does the data feel like it has a normal distribution around that slice? Does it feel symmetrical? In this case, does it feel symmetrical above or below the blue line, the linear regression? And again, that seems reasonable for assumption 3, the normality. So therefore, with these assumptions in place, and we've taken time to consider them, the posterior model should be able to simulate the ridership data. Thus, recall from the RStan ARM package, we are able to make a generalized linear model equation, bikes data. We have a lot of assumptions about using Gaussian approaches or normal distributions. We have in the past prescribed these distributions for the priors, and we're building our Markov chain Monte Carlo approximations. Remember that this bike model produces thousands of possibilities for the bike models, where each model has an intercept and a slope for the for the model as long as an estimate for the standard deviation. We could then use that bike model, or say from just this one instance of those regression coefficients, store those as beta naught, beta 1, and sigma temporarily. We could simulate what that would do with our data. Because of the assumptions, we are at least being mindful of the assumptions. Remember that we are doing our simulations with a normal distribution along the way. And we find that at various temperatures, here on the right are the results from the simulations. And in the middle would be the results along the linear regression line itself. So thus, part of what's going on is not only are we getting our predictions on the linear regression line, on the blue line in the image, we are also getting a sense of what could happen above and below the blue line in our simulations. The folks in the previous cohorts made graphs like these, and I thought that the use of this theme here, in this case the 538 theme, was a nice choice. Here, as they have implied, the simulations, the posterior simulated data set is in the light blue, and the actual observed relationship is in the dark blue. Apologies that the colors are a little hard to see, but in the light blue, the simulation, we have a bell curve that's coming from our assumptions on normal distributions. But the real life data, it's debatable, or you can argue one way or the other whether or not that looks like it fits the normal distribution, that if it fits the bell curve. When you have more complicated data, say for instance, if you have more than one predictive variable, looking at things with graphs like this might not be reasonable anymore. So you would then be quickly motivated for other ways to check or reassure yourselves that your model is reasonable. And in this textbook, we are calling this the posterior predictive check. The folks who created the Bayes plot package has a function that will help us with this. We look at the posterior predictive check in our bike model, which for the sake of this slide, we'll look at 50 of the 20,000 simulations. And thus, with the thoughts in mind, we could see in the light blue, the 50 simulations, which each are bell curves or pretty close to it. And then the dark blue bold line, that was our actual data. So once again, we could look at an image because we have one predictor variable, and this two-dimensional image will help us for now. This part of the process is similar to how we might view trace plots when looking at other aspects of our MCMC simulations. Fortunately, if we find ourselves dealing with situations that might not align as well with the assumptions as the current case study does, the authors do give some advice on how to deal with wrong models. So I'd like to mention them now. If assumption one, the independence, might be faulty, we will later consider processes such as hierarchical Bayesian models later in Unit 4 to handle situations such as dependent group data. If assumption two, linearity, might be faulty, perhaps a transformation can help, such as a logarithmic scale for x, a log scale for y, or maybe a log-log scale for both x and y could help. And then in assumption, if assumption three might be at fault or might not seem to be right for the situation, we could consider a different distribution as well, such as the Poisson binomial or negative binomial distributions. Like a lot of machine learning processes, we want to get a sense of how accurate our models are, especially after doing many simulations, or as we'll see in just a bit, many different cross-validation splits. So we'll look at three approaches here on this page, on this slide, to evaluate the predictive quality. Perhaps the quickest and most apparent at first is the median absolute error, or MAE. And what that's doing, maybe I could find it. What the median absolute error is doing is taking the differences between the observed and the simulation and finding the difference between them. And then taking the median of all those results and outputting a number. Now, in our example, what was on the horizontal axis was temperatures in Fahrenheit, what was on the vertical axis was the number of bicycle riderships. And that could, just by the sheer units, have numbers that feel relatively big or relatively small themselves. Thus, sometimes you want to rescale the MAE to maybe, in a point of view, get a better sense of the error. Rescaling is also called relative error. The prediction summary function running on the bike model. This is a wrapper function that's, by the way, doing several simulations. So if you were looking at the beginning of the video, apologies, I was waiting for some code to compile, and a lot of it was this right here. So keep in mind, if you're trying out these Bayesian methods, that these simulations may take some time on your computer, maybe on the order of a couple of whole minutes. A couple more metrics that we see provided are called within 50 and within 95. That's the proportion of data that fall within those posterior prediction intervals. Thus, if we're asking for a 50 percentile posterior prediction interval, we see that about 44% of the data is there. So what we're looking for is within 50, we're hoping for a number here that is also close to 50%. Similarly, looking at the 95 percentile posterior prediction interval, we see about 97% of the data there, but moreover, we're hoping for a number that is close to 95%. Following along with calculations we did in the last chapter, suppose that we focus on the bicycle ridership when we have an outside temperature of 75 degrees Fahrenheit. We could use the coefficients from the bicycle models that were produced earlier, find values for mu from the linear regression, but also then find various other predictions we called y nu, once again assuming a normal distribution around a mu and sigma that was produced from the bike models. And what we're looking for, kind of similar to thoughts you might have seen in null hypothesis significance testing, we do have a distribution. That's our posterior distribution. In particular, on a 75-degree day, such as October 22nd of that year where they collected the data, they observed 6,228 riders. That's the vertical line. And we're kind of asking ourselves, is that reasonable? I mean, for one thing, our model has a mode maybe closer to 4,000 riders. So briefly thinking about the hypothesis test point of view, we would look at the vertical line, look at the area to the right in the right tail, and get a sense if that's a lot of area or little area. Sometimes in the hypothesis point of view, that's of course called the p-value. But for here, in the Bayesian point of view, we're going away from the notion of p-values, even though I myself might be thinking about it quite a lot. But nevertheless, we are considering the area to the right of that vertical line, and if that's a little or a lot, and how we feel about the usefulness of the model and the current data. I went on quite a tangent there. Federica, did you have more to say about this or other thoughts on the matter?
Okay, this one is basically focused on 75 degree per day, and in the month of October. And why this vertical line, this geometry line, so this 6,228 is the average. So it is not centered as we expected. So we can say that so we can say that temperature influence the number of rides, and if you scroll a bit down, because this is the density to show that the density in this number of simulation is normal distributed, and then where is the location of the mean average, the mean value basically of the observed values. You can see the difference from the simulated data and the observed values. And yeah, so, and it says more about this, because this is again the same plot that we saw, but now you can see that there is this shadow line. So you can see what could be the variability, and so we use this PC intervals function on rides and predictions and the temperature. And it releases basically all observed values with their prediction and a range of variability. So you can have, so in fact, they take them all. Basically, there is a band beside just a few outliers. And so it says the posterior predictive medians, which are the light blue dots. So those one here in the very center. Okay, so this is the line, the regression line, and 50% prediction intervals are the wide short blue bars. So these blue bars. While the 95 prediction intervals are the narrow, long blue bars. Okay, so the opposite. So this is the prediction interval, and this is the 50%. The other one is 90%, obviously, because it's yeah. Okay. Why the dark blue dots are the observed data, the observed points.
Yes. Thank you. I appreciate your insights and your thorough description of the posterior predictive intervals and intervals of how we look at the data and the regression line. Thank you. Borrowing from other situations or other book clubs or classes, when we think about machine learning, in broad terms, in the case study, we would ask ourselves, if we took these models and applied it to maybe another year of data, so a different year than 2012, sorry, 2011, or maybe we applied it to a situation in a different city, how well would this do in that new situation? We would have to worry about what's called the variance of the model itself, or the bias variance trade-off. One way to deal with that or anticipate that in advance is called cross-validation, where we split the model into training and testing sets in a certain prescribed way and do that a few times, maybe about 10 times, and we'll build a prediction summary in this cross-validated way. In other words, we're getting the same metrics that we did before, the median absolute error, the rescaled one, the relative error, and we're getting those 10 over 10 times, the 10 cross-validated faults. We could then, of course, once we have a list of 10 numbers in each column, find the average and at least be assured that when we try to generalize these processes to newer situations, that we would have numbers or in the metrics that look like this. Now, at the moment, if you're curious about, well, what does this number mean? Like elsewhere in model statistics, sometimes it's not about the individual number itself, but whether or not you have multiple models. Say in this particular example, we're using a lot of normal distributions as our assumptions to make our model. Maybe someone else is using beta distributions, maybe someone else is using Poisson distributions. You come together and compare results, and these numbers help you more when you compare results with other models. But nevertheless, for right now, these numbers here are useful in my opinion. Remember that we're hoping about 50% of data falls within the 50 percentile posterior prediction interval. And likewise, for 95, we're hoping for about 95% of data. Another measure, which may be a bit more mathematical, is called the expected log predictive density. At least in theory, it's looking at the density plots, literally the curves, and we're dealing with normal distributions today. The motivation for logarithms is if you're dealing with thousands of calculations, you want your computer to handle it, and the logarithms help. The idea, and I'm going to try to say this as simply as possible, is that if we plug in new y data, where does it fall on our distributions, on our likelihoods? And we're hoping to be in a position, comparing the left and right graphs, we're hoping to be in a position where we're higher up on the curve, where we have more likelihood. So in this point of view, very quickly, the scenario 1 on the left would be considered to be better than scenario 2 on the right, simply because we're at a higher location or a larger y value vertically. The Lu function, also a part of this overall RStan ARM package. does leave one out cross-validation, which surprises me because leave one out cross-validation as opposed to a k-fold cross-validation. Leave one out cross-validation takes a lot of computational time, though it may be a preferred method for some machine learning analyst. So this code takes a while to compile as well, so just be mindful of that. But what it'll do is it'll produce an estimate in this metric ELPD. And once again, I just want to note that while this one number itself might not mean much to us right now, it's very context dependent because it's coming from a lot of calculations that are themselves are done with the temperature data and the ridership data. So this one number itself might not mean much at the moment, but if you and your colleagues are comparing different models, then these numbers would then be very helpful for a quick comparison or a quick assurance of which model may be better in the situation. At this point, the authors offer a bit more advice when dealing with these posterior predictive accuracies. And if you're a researcher and wondering where to go from there, you could, of course, collect more data. You could use more or different predictor variables. Today, we had the one predictor variable for the temperature in Fahrenheit. And remember in previous chapters, we talked more about the MCMC Markov chain Monte Carlo simulations. And we also have to consider how good the model is today. So we would double check whether or not the MCMC simulations approximates the model itself. And then finally, what we did today in consideration of does the model fit? Remember, it's a broad question. Not only are we looking at the graphs or the metrics on the posterior distribution, but we are asking ourselves to think, well, wait, were the assumptions reasonable? That is the independence, linearity, and normality assumptions that we looked at today. Is the model fair? Does it work well with the situation? And perhaps we might even have some surprising biases that are coming from the data collection and how we carry out the machine learning calculations. And then what we did afterwards, after the simulations, was ask ourselves, does it produce good predictions? And we had some checks on the posterior distributions that way. All right, so with that in mind, having spent time on this chapter, just being really careful about how we look at regression models. It looks like what we'll be doing next week in the next chapter is then extending the regression model, asking ourselves questions like, what if we have more than one predictor variable? Or what if we have slightly different point of views than the linear regression itself? So that will be it from me from today.
Thank you.
Anything else, or we'll see you next week?
See you next week.
Okay.
Bye.
Bye.